Let's take a look at the test 2 review, and I also want to give you some tips to be the most successful. First up, let's remind ourselves that test 2 starts with dimensional analysis, and that's the process of converting from one set of units to another. Okay, the way we do that is first we write the two givens, where we start and where we're going to end, and then we kind of fill in the middle with conversion factors. Now, our goal with conversion factors is to cancel out the units, but each one of those factors should be equivalent on the top and bottom. In other words, 60 seconds is equivalent to 1 minute, so I can use it in the middle. 12 inches is equivalent to 1 foot, so I can use it in the middle as a conversion factor. First one is just to get us started here. We've got 27 minutes to seconds, 27 minutes to seconds. So in order to do that problem, what we're going to want to do is we're going to want to write our given, what we start with, 27 minutes, and where we're headed. We're headed to seconds. So we're looking for the blank seconds. That's what we're trying to do. Now what we're going to try to do is connect those two ideas, minutes and seconds, those two units, using conversion factors. Now I want to cancel out minutes and I want to get seconds. Now I do know that I can put minutes on the bottom and that will cancel out the minutes. So what is equivalent to 1 minute in seconds? 60 seconds. Then what we're going to do is we're going to multiply straight across the top and bottom. And that will give us 1,620 seconds and 1 on the bottom. I want you to notice that the minutes on the top and the minutes on the bottom canceled out. So it's not 1 minute, it's just 1. It's just a number. The units canceled out because we had minutes on the top and bottom, which means since the minutes cancel out and we're just dividing by 1, we just end up with 1,620 seconds. And that's our answer to how many seconds there are in 27 minutes. To take a little bit bigger look, we're taking 12 weeks to blank minutes. So we're going to start writing out. What are we starting with? We're starting with 12 weeks. Where are we headed? We're headed to minutes. And so we're going to fill in the middle with our conversion factors. The first thing we're going to want to do is we're going to cancel out weeks with week. And so 1 week, how can we make that into minutes? I don't know how many minutes are in a week, but I can make it smaller. Minutes is getting smaller, so I'm going to make it smaller. What's smaller in a week? Days. There are 7 days in 1 week, so that's what I'm going to use for my conversion factor. Now, at this point, I want to connect days to minutes. Again, I don't really know how many minutes are in a day, but I do know I can keep making it a little bit smaller. So 1 day is 24 hours. And then finally, I can get to minutes because I can cancel out hours with minutes. So I know that 1 hour is 60 minutes. Now at this point, all three of these conversion factors in the middle are equivalent to 1. 7 days is equal to 1 week. They're the same on the top and bottom in value. What we're going to do is we're going to multiply straight across the top and straight across the bottom. And since the bottom is just 1, we don't really have to divide by 1. And so what we end up with is 120,960 minutes in 12 weeks. Notice that we wanted to put however we needed to do to cancel out our units. The only units left is the one we wanted to be left. Converting measurement, when we're talking about from metric to customary, we're going to want to use a conversion factor. So in this one, we've got a couple we can use. We're converting from 23 pounds to however many kilograms. Now, we have two conversion factors that they connect pounds and kilograms. You could use either one. We just want to use whichever one makes sense for the situation. Either one would work. We just want to make sure that if we're going to convert to kilograms, that means we want to cancel out pounds. So we're going to put the 1 pound on bottom. You could have put the 2.205 pounds. We could have used this one, but instead I just used the 1 pound on bottom. That way I'm just dividing by 1. And on the top, I'm going to have the kilograms. It tells me that. So I'm just putting my conversion factor right in there. We're going to multiply that. And guess what we get? We get 10.4328 kilograms over 1. Remember, pounds have canceled out. And so the reason I picked to put it over 1 is because now I can just say, boom, 10.43 kilograms is my answer. Converting the following temperatures from Fahrenheit to Celsius or vice versa is one of our basic skills that we need to do because we live in a world where some countries like the United States use Fahrenheit and some countries like Australia use Celsius. And so we need to be able to use either one of these formulas, but what we're just going to do is we're just going to plug them into those formulas to get the other thing. So if we have Celsius and we want Fahrenheit, we're going to plug it into the Fahrenheit formula. And if we have Fahrenheit, we're going to plug it into the Celsius formula. So for example, A would be C, the Celsius for A would be 25 degrees Fahrenheit minus 32 over 1.8. Now, if we're going to use something like C of negative 20, I want to convert that to Fahrenheit. So we're going to say Fahrenheit equals 1.8, and I have negative 20 for my Celsius plus 32. And that, whatever that calculates to, is going to end up being our answer. Let's look at another conversion one. Now, this one's a little involved because what we're trying to do here is we're trying to take what we have, which is 1 liter and 23 kilometers. That's in our problem. But our problem actually also tells us another fact. It tells us that there's 125 or 1.25 euros per liter. So there's two facts that they give us. And what we're looking for when we have two facts like that, we're just going to treat them just like we would conversion factors. What we're trying to turn it into is dollars per 200 kilometers. Okay, how many dollars would it take to go 200 kilometers? So let's see how we would go from liters and euros. Now the nice thing is, since I already have two things, I put liters on bottom just so it cancels out because I don't want liters in my answer. But if I just take that, I would end up with euros and kilometers. I want it in dollars, so I'm going to use my conversion factor for dollars and euros. 1 euro is 1.256 US dollars. So now I can cancel out my euros. And from there, I'm just going to multiply straight across. Now this time I didn't have just 1 on the bottom the whole time. I actually had 23 times 1 times 1. So at this point we get 1.57 US dollars is how much it would cost to go 23 kilometers. But I don't want to know how much it costs to go 23 kilometers. I want to know how much it costs to go 200 kilometers. So what we need to figure out is, what do we need to multiply 23 by to get 200? And so I just did the quick division here, and I ended up with 8.696. That's what I need to multiply by, because I just divided 200 by 23. That means I need to multiply it by 8.696 to get to 200. And then I would get the answer to my question. I want to know how many dollars for 200 kilometers. But in order to do that, I also need to multiply on the top and the bottom by the same amount. And so in addition to the kilometers being multiplied by 8.696, the dollars are also multiplied by 8.696, which means our final answer on this one is $14.08. Convert to Fahrenheit. This is another convert to Fahrenheit. They have a slightly different formula. It's just written differently, but it's really the actual same formula if we were to move things around. This one actually gives us Celsius, and we want to convert to Fahrenheit, so we're going to use the Fahrenheit formula. Fahrenheit equals 9 over 5 times Celsius. In this case, we got negative 50 plus 32. And from here, we can go ahead and do a little bit of math, and I get negative 50, and that would be negative 90 plus 32. And so I get Fahrenheit for negative 50 Celsius is negative 58 degrees Fahrenheit. Scale ratios for maps, they usually tell us 1 centimeter to 1 kilometer, whatever. You'll see it written on a map that we say, well, 1 centimeter on the map represents 100 kilometers. But a scale ratio should be written, or could be written, without units at all, okay? And the way we do that, and the way we create a scale ratio, is we convert both of them to the same unit. So 1 centimeter and 100 kilometers, if I wanted to convert them to the same unit, I could convert them both into meters. So 1 centimeter is not as big as 1 meter, right? They're different. A centimeter is smaller. In fact, I'd have to divide by 100 And so I get 0.01 meters is 1 centimeter. 100 kilometers, that's more than a meter. So it's not just 100 meters, it's 100,000 meters. A 100 kilometers, each kilometer is 1,000 meters, so that's 100,000 meters. Now, so what is our ratio? When we have these two, I would prefer it to be the ratio of 1 to something. So I want the first number to be a 1. Right now, the first number is not a 1 because it's 0.01. What do I need to multiply by? I'm going to multiply by 100, which means I'm also going to multiply by 100 on the other one. So it's 1 to a 10 million ratio. So everything has been shrunk down. 10 million is shrunk down to just 1. So 10 million centimeters is shrunk down to just 1 centimeter, or 10 million meters is shrunk down to just 1 meter. Let's look at another one. This one is a little bit less of a crazy scale. We have 1 centimeter and 50 meters. Now I'm going to do the same thing. I'm going to try to convert this into the same thing. Since this is already in centimeters and it's already 1, I'm going to try to convert this one to centimeters. Okay, so how many centimeters are in each meter? Well, there's 100 centimeters in 1 meter. So in 50 meters, I'm going to do 50 times 100. So there's 5,000 centimeters in 50 meters. And so our ratio here is 1 to 5,000. Okay, so what we're saying is the scale is 1/5000th. Let's look at another scale ratio problem, but this one's a little bit different. This is one of those things that you might see in a documentary where they talk about the Earth being really, really old and human written history's not that old. And so the first question says, suppose the entire history is represented by a 10-meter long timeline. What is the distance that represents 1 billion years? So the entire history is 10 billion. So I would say 4.5 billion. That's 10 meters. And the follow-up question is, well, what is 1 billion meters? Or 1 billion years? It's not 1 billion meters. It's going to be less than 10 meters. And so all we're going to have to do, if we don't find x meters, notice that my billions of years and my meters line up. They're in the same place. And we're going to solve that proportion by going ahead and cross multiply and divide. So we get 4.5x equals 10, and so x equals 10 divided by 4.5. Now, that's part A. Part B says, how far from the end of the timeline does human written history begin? Now, human written history is not a billion years. It's only 10,000 years. Now my problem is I can't just go ahead and cross multiply and solve this one as it sits, because this one is written in years and this one is written in billions of years. So we're going to make them both into years. So instead of saying 4.5 billion years, we're going to say 4,500. That'd be 4.5 million, but I want 4.5 billion. And then we can cross multiply and divide. Okay? Talking about mortality rate, suppose that many people died and the population of a country is this much. They want to know what is the mortality rate in deaths per 100,000. So the way we do that is we do the total population. We do the group that we're looking at, which in this case, the deaths. And whatever we get, instead of just saying that ratio, we want it per 100,000 people. So we're going to multiply those together. And so deaths is going to be 586,250 divided by 264 million. Again, pay attention that we're writing in the same units. 264 million means I'm going to go ahead and write 1, 2, 3, 1, 2, 3. So I've got 264 million written out. And then I'm going to multiply it by 100,000. And when we type that in our calculator, we end up getting the answer we're looking for. Your car gets 27 miles per gallon, 27 miles per gallon per 1 gallon. How much does it cost to drive 360 miles when gas costs 340 per gallon? Okay, so the first question is, how many gallons would it cost to go 360 miles? How many gallons? So I'm just putting a question mark there. To go 360 miles. Well, this is just going to be a straight proportion. I can go ahead and cross multiply and divide. And when I do that, what I'm going to end up getting is 360 divided by 27 gallons. So whatever that ends up being, when I cross multiply and divide, I get how many gallons. But the question didn't say how many gallons is it going to take. It says how much it's going to cost. I also know that the cost per gallon is 340. So if it costs me 1 gallon, it's going to be 340. If it costs me 2 gallons, it's going to be 680 and so forth. So I know I need to multiply by 340 in order to get my answer. And when I type that in, I will get an answer. I want to make sure I use the right number of decimal places because we're talking about money. Consider the following exam question. So this is one where somebody has already solved it. And they said they went into a candy store that sells chocolate for $7.01 per pound. And they want to buy just a piece of it. Okay, they don't want to buy $7 worth of chocolate. And so they look at how much they have, and they've only got 0.17 pounds. And so their math is that it'll only cost them 2.4 cents before tax. And they think, oh, I'm just going to give them 2 cents. Now the question is that the right answer? Well, no, that's wrong. The follow-up is, why is it wrong? Or how would you do that the right way? Okay, so they did something wrong because 2 cents for chocolate is too cheap when they're selling it for $7 a pound. We need to make sure that we're selling it for the appropriate representation. So I'm going to do this with a proportion. I'm going to say $7.01 per 1 pound. And this time we have how many pounds? 0.17 pounds. Notice I put the pounds with the pounds. They're both on the bottom. And what I want to know is what is my dollars right here, okay? And we can cross multiply and divide. So if you look at what they did, they actually took 701 and they divided 0.7 when we should have multiplied. Let's look at an electricity problem. We have the company charges 15 cents per kilowatt hour of electricity. So the first part we have is, let's say we have a light bulb, and the light bulb is a 60 watt light bulb, and that means it uses 60 watts each hour, and then we use it for 13 hours each day. So I'm going to go ahead and figure out how much electricity it uses in a day. So I do 60 watts times 13 hours, and I end up with 780 watt hours. Okay. They told me that they're going to charge me 15 cents per kilowatt hour. So if I multiply that by 0.15% per kilowatt hour, you'll notice that it actually doesn't cancel out because we have watt hours on the top and kilowatt hours on the bottom. So we need to kind of do some math here, okay? So what's the difference? Well, the difference is that a kilowatt is 1,000 watt hours, okay? So in other words, we can also say that 780 kilowatt hours, or watt hours, is equal to 0.780 kilowatt hours. And then we can multiply that by that 15 cents. And what we're going to get is that it costs us, a few cents a day. Let's say 11 or 12 cents a day. You'll notice that if we wanted to save money, we could replace our 60 watt light bulb with an LED bulb that is just as bright, but it only uses 10 watts. Okay, so how much would we save? Well, if it only uses 10 watts and we're using 60 watts, we're going to save 50 out of 60. We're going to save 5/6 of our costs. So in order to calculate it, we're going to go ahead and multiply our cost per day times 365 days in a year. And that would give us our total cost for the year, but we're actually going to save most of that because we're going to switch to a more efficient light bulb. To end up with the units of speed, when we talk about speed, what do you need? Okay, so when I say speed, what are some examples of speed? Well, we've got miles per hour. You might also have meters per second. You could have, what's another speed measurement? Kilometers per hour. And so what I want you to notice is that whenever we have speed, that is distance, how far you're going, divided by time. So speed is the measure of how far you go and how quickly you get there, okay? In a certain country, the life expectancy for women in 1900 was 47 years, and then it turned into 80 years. So it went from 47 to 80 years. So it went up. How much did it go up? So it went up 33 years. I just subtracted those, right? So what percent increase happened? Well, our percent increase that happened, what we need to do is we need to take our new minus our old, 80 minus 47, and divide by our old, or our original amount. And if we do that, we end up with the 33, the amount it went up, divided by 47. Okay, so it's, sorry, I'm going to use my calculator here. That's going to give me my percent increase. If I use my calculator, I get 33 divided by 47. And so that's 0.70 or 70%. Okay. Now here's the catch. If it says it's going to keep increasing for another 100 years. If it keeps increasing at the same rate, does that mean it's going up the same number of years? Does it go up 33? Well, no, because it's not going up by 33 years each time. It's going up at the rate of 70%. And so we need to figure out what is 70% of that 80. So we can do that pretty quickly by doing 80 times 0.70. And so that's 56 years. So does that mean that the life expectancy will be 56 years? No, that means we add 56 years, and so that we end up with 136 years. Suppose that a certain basketball game, the athlete earned $23,500,000 to play 80 games, and they only take 48 minutes to play a basketball game, assuming they don't go to overtime. How much did the athlete earn per game? So first, we'd say, well, this is easy math. We just say they took the 23,500,000 and divided by 80, because that's how much money they made per game. However, the athlete might say, whoa, it's not quite that simple, because I played every minute of those games. And so we might need to say, okay, so if that's how much they made per game, then we take that and we're going to multiply that by, or divide that by 48, because that's how much they made per minute. All right. But some athletes don't even play the whole game. They only play 2/3 of the game. So what we're going to do is we're going to say, well, I don't need to divide it by 48 minutes. Instead, I'm going to take that amount and I'm going to divide it by 2/3 of a game. So 2/3 of 48 is 32. So they only played 32 minutes. Well, then we're going to divide that, and that will give us that. Now, the last part is that the athlete will say, no. you can't just say for the minutes I was there, because I worked for every game. And let's say that on average, they practiced for 33 hours and played every minute. What would their hourly salary be? Okay, so we're going to work this out here. So how many total hours did they work? Well, for each game, let's factor this down to hourly salary. So they started with this much money for the year, but that's for 80 games. Okay, but each game cost them 33.8 hours. Okay, why 33.8? Because of 33 hours for every game in practice, plus the 48 minutes or 48 out of 60 for the time they played in the game. First glance, this looks more difficult than it is. We've got 160 micrograms and it's in solution. Okay, so we have 160 micrograms. That's what we want to give. We want 160 micrograms. But the drug is 500 micrograms per milliliter. So the question is, how many milliliters should be given? So again, this looks really complicated, but when we write down what we have and what we're looking for, this is really just a straight division problem. So we end up with 160 divided by 500, or 0.32 milliliters. Let's take a look at the metrics that we can use in different situations. It's important that we know our metric units, okay? So a few of the ones right off the top of my head are millimeter and centimeter. You sometimes see decimeter, but we're not going to use that one too much. We're going to say meter. You might even see kilometer. And those are big metric distances, okay? But I want you to know that there's the other ones, that we could have all the same prefixes with weights. And you should have a roundabout guess about how big each one of those is. For example, a paperclip is probably going to be measured in millimeters. It's really small. And a width of a dime, probably millimeters. You could maybe say centimeters. A dime might be a centimeter wide. I don't know. If we're talking about the width or the thickness, then thickness should be definitely millimeters, right? A tall floor lamp might be measured in meters. It could be 2 meters tall. The width of a room would be meters, usually. A road race, so if you're racing on the road, you would expect it's probably with cars or bikes, so we're going to say kilometers. The wingspan of a butterfly is probably in centimeters, probably fair enough. But you might even say an eagle is in centimeters or in meters. I think eagles can get pretty big, so I'm going to say maybe in some meters. Shoe size, a meter would be too big. Everybody has shoes that are less than a meter big, so we're going to say a little bit smaller, centimeters. The width of a window, again, a meter is probably too big to measure most windows, but there are some windows that it's not too big, so depending on the situation. Now, I want to stop for a second and focus on this last one, because when we start talking about different dimensions, we talk about floor space of a tent. You might say floor space of a tent, it could be 3 meters by 2 meters, and so you could say it's meters. But the truth is, it should be meters squared, because when we're talking about area, we want squared dimensions. If we're talking about volume, we want cube dimensions. So I want you to watch out for that. I don't want you to get it wrong just because you picked the right, but you weren't paying attention to the units and the dimensions. House, 21 meters by 9 meters. Okay, so we've got a house and it's a rectangle. And it's 21 meters by 9 meters. And I can find the area of that house, I multiply those two together, and I get 189 meters. Again, we just want to remember that that's the second dimension, so 189 meters squared. Now, the question is actually saying, listen, we have this house, but we also have a walkway around the whole house. And so that walkway around the whole house kind of gives us a bigger rectangle. Can you kind of see how, if we imagined that the whole house had like a big rectangle, if it continued the walkway underneath the house, like the concrete, then we could have a bigger rectangle. So the question is, how big is that bigger rectangle right now? So if the walkway is only 1.2 wide in this range, but we notice it's 1.2 wide on both sides, 1.2 plus 1.2, that's 2.4. So it's 2.4 meters that is adding to each of our dimensions. So our rectangle is going to be 21 plus 2.4. So that's 23.4 meters. And 9 plus 2.4, so that's 11.4 meters. And so our big green rectangle, if we were to fill in the whole thing, would be those multiplied together. So I'm going to get out a calculator because I don't know that off the top of my head. So I'm going to say 11.4 times 23.4. And so the big one I got was 266.76. And it's going to be meters squared because we're talking about area. So what is the question? The question is find the area of the region covered by the house and the walkway. Well, guess what? That is what we just found. But let's say we don't want to include all the part that's both green and red. Let's say we want to take this part out. Well, how are we going to find that? So for part B, all we're going to do is we're going to take that 266.76 and we're going to subtract the 189 that the house is covering. And that would give us our answer for B. It's still going to be in meters squared. Quick view of these notes. Now this is going to look pretty basic, okay? But what we're focusing on is actually applying this. So a few things I want you to know is that in order to convert fractions to proportions, we're just going to divide, put it in a calculator. Proportions or decimals can be turned into percents by multiplying by 100 or moving two decimal places. And then the other thing is I want you to remember that is over of is our default here. If we see it of, we're going to usually put that on the bottom. And the other thing is we're going to usually put the whole on the bottom as well. So these are our setups. Let's go ahead and jump right into some problems. This is an example of the type of solving an unknown value in a percent proportion. So the setup is going to be part over whole equals percent over 100. So let's start just by saying we have part, we have percent. So let's fill it in. We have 10 over whole equals percent is 2 over 100. So the part I don't have is whole. So I'm going to put an X right here. That's the part I don't have. And now we're going to solve this proportion like we do any other proportion. I'm going to go ahead and multiply these, and I'm going to get 2x equals 1,000. And then I'm going to divide by 2, and I get x equals 500. So remember, we're multiplying diagonally, the ones that aren't a variable, and then we go ahead and divide by our coefficient there. Let's try it again. This time we're finding the whole, okay, just like last time. And we know that the part is 63, so I know that's on top, and the percent is 15. And percents are always over 100. So what I don't know is I don't know this whole, so I'm going to cross multiply and divide. And so if I do that, what I'm going to get is x equals 6,300 divided by 15. And then if it wanted as a decimal, I could go ahead and just type that in as a decimal and get it my answer. Pay attention to what you're looking for on this. If you're looking for a decimal or a fraction, just pay attention to what it's wanting. For this one, it looks maybe like a little bit different setup, but I want you to notice we have 160%. So we're still going to go 160 over 100. We have percent. and then it says of 300 miles. So we need to match up that percent side over here. So where are we going to put the 300? Well, our trigger word is that of, okay? The of kind of gives us a hint that the 300 is what matches up with the bottom, okay? 300 would match up with 100. So now we go ahead and put an X on top. From there, we can cross multiply and divide, and we end up with X equals 480. If Rebecca makes $220 per week, and 23% of this is 100% of her money. If 23% of her money is withheld, how much money is withheld? And so this is going to be a pretty straightforward cross multiplication. Notice that I put both the monies on the left and the percents on the right. You could have done it top and bottom, but everything needs to line up. This matches up with that. It also matches up with that. In the following statement, express the first number as a percentage of the second number. So the first number we get is 4 to 900, and I want it as a percent of the second number. So 35000, and I'm just going to type those into my calculator just like that. 4 to 900 divided by 3500, and what I got was 123%. Well, I actually got 1.23%, and 1.23 is a decimal, and I made it percent. All right, we've got some ratios in words. These are some basic ones. 33 out of 100. That's a ratio in words, but we could write that as a fraction as 33 over 100. So as a decimal, if we type that in our calculator, we get 0.33. As a percent, we get that 33%. When we look at 55 out of 100, or 0.55, as a percent, again, we just move it 2 decimal places. So we say 55%. And as a fraction, we could write it as 55 out of 100. Now, if we had to simplify that fraction, we could do it, okay? Because we could take 5 out of the top and bottom, and that would give us 11 over 20, which is our simplified form. 33 over 100, we didn't need to simplify because nothing went into both of them. 12 out of 100, okay? As a fraction, we could obviously write 12 out of 100, but we could also simplify because we could take a 4 out of the top and bottom, and that would give us 3 out of 25. Oh, not 24, 25. Now, as a decimal, we want to think back at that 12 out of 100 means we're going to put it 0.12, and as a percent, that's going to be 12%. Okay, so working in and out of fractions and decimals, we sometimes have to do the extra step of simplifying the fraction, but it's pretty straightforward. Compute the total cost per year of the following pair of expenses, and then complete the sentence. On an annual basis, the first set is blank percent of the second set. So the first thing we need to do is annualize this. $12 every week. We need to multiply by how many weeks there are. There are 52 weeks. And so that's going to give us our number there. 134 per month, we need to recognize that 134 each month, we need to multiply it by 12. Now, since we're putting it as a percent, that means that on top, we're going to put the first, since it's a percent of the second. So I'm going to say 12 times 52 divided by 134 times 12. And let's see what we get. I'm going to type this in my calculator. 12 times 52. And I got that, and I'm going to divide it by 134 times 12. And I got 0.388. But if I want to put it as a percent, that means I'm going to put 38.8%. We have some of the same percent problems and ratios that we had in Unit 8. So we still are going to talk about percents and parts and percent increase and percent decrease. But what we're going to do this unit is we're going to add a little bit more on the statistic side of things. So we're going to talk about things in terms of frequency, cumulative frequency, and relative frequency. So to give you a quick introduction to that, I wanted to show you this frequency table here, okay? And what we have here is we got a table from a chart, a table that shows the frequency of people in each weight. So we have 22 total people, and there are 3 people that weigh in this range, and there are 6 people that weigh in this range, and you'll notice that it adds up to 22 because that's the total. Okay, that's what frequency means. It's just what do we have in each category. The cumulative frequency is a little bit different because we say, what do we have in the category, or what do we have in the category before it? So in this case, the cumulative frequency is going to be not just 6 for the second part, but 6 plus what we had before, which is 3. So instead of just being 5, we're going to say 5 plus 9 is 14. And then 6 plus 14 is 20. And then finally, 20 plus 2 is 22. We also have a relative frequency, okay? And whenever we see relative, really what that means is we're going to divide by our total. And so each one of these relative frequencies are the are the frequencies over the total. So this is 3 over 22, and that's where we get the 13.64%. Those are decimals. We could also notice that they do add up to 1. It is possible that they could be off just a little bit if they rounded funny, okay? So they could be off just by 1%. So if bridge A is 2,100 feet and bridge B is 4,600 feet, bridge A is shorter. How much shorter is it? Okay, so what we're going to do is we're going to subtract the 4,600 minus the 2,100, and we get 2,500. But it actually wants percent shorter. Okay, so I need to put 2,500 on top, and on the bottom it says shorter than the main bridge B. So I'm going to put bridge B on bottom, so I'm going to put 4,600 right there. So if I go to my calculator, I say 2,500 divided by 4,600, and what I got is 54% shorter. If you saw an advertisement that said, by turning off your lights and closing your windows at night, could you save 130% on your energy bill? Hopefully, alarm bells would go off, because this would be like going to a store with a 130% off coupon. In that case, the store would have to actually give you money because you have saved so much. You saved more than 100%. So since you can't really save more than 130%, more than 100% of your electricity bill just by turning off your lights and closing your windows, then I'm going to say that this couldn't possibly be true. A farmer recently purchased her neighbor's farm. Before the purchase, the farmer owned a total of 355 acres of land. After the purchase, she owned 496 acres of land. What is the percent increase? Now, when we talk about percent increase, it's a percent of change. We need to make sure the number we put on top of our fraction is the amount of change. So she started with 355. She had 496. We're not just going to put 496 on top. That is the final amount, but that's not how much it changed. We have to subtract what she started with. And then we always divide by the original amount. And then that will give us a decimal, okay? Now, since it asks for percent, then we're going to have to do something to turn that decimal into a percent. So we have 0.3971. If I wanted to turn that into a percent, I'd need to move this 2 decimal places, or just simply multiply by 100. So 39.71%. Let's look at another example with percent and percent increase. And the point I want to make with this problem is the difference between a percent change and percentage points. So we have an absolute change in percentage points and a relative change in a percentage. Now, a lot of times you'll hear stats on the news and they won't really specify whether they're talking about an absolute change of percentage points or a relative change of a percentage. we use this when we have percents that we're talking about. So in this case, it went from 68 to 82. So we're going to go ahead and take the 82 and subtract what it started at 68. And that would give us 14. Now that's 14 percentage points increase. That is not an increase of 14%. So that's a percentage point increase. I just subtracted. So in absolute terms, that's 14 percentage points. Notice I didn't write the percent symbol. Now in relative terms, I take that absolute and I divide by what I started with. And when I do that, that percent is what's going to go right in there. I'm going to go ahead and use my calculator and figure this one out. I'm pulling out my handheld calculator. 14 divided by 68. And I got like 20.20588. And it kept going. But I need to round it to the nearest tenth. That means one decimal place. So after I multiply by 100, I'm going to get 20.6%. So notice that those are different because percentage points are not the same as a percentage. 60% of the hotels in a certain town have a restaurant and 10% have a swimming pool. Could you then say that 70% have one of those two? So we know that 60 plus 10 is 70. So is this a fair conclusion? This is only a fair conclusion. It's not, unless there are no restaurants that have both, unless they're mutually exclusive. Mutually exclusive. In other words, none have both. One example could be that every hotel with a restaurant also has a pool. Okay, so then what's the percent of hotels that have a restaurant or pool? It's still 60%. We don't actually make any more hotels because they overlap. This is one of those deceptively tricky problems. So I want to show it to you because usually the first time you look at this problem, you might think about it backwards. And that's because it's written backwards. So it says the diner's frequency would add a 15% tip. And so when we go ahead and pay, if we got and we price the meal and we charge $31.05, including tip, that's including tip. How much was the tip? Okay, so if that's including tip and we want to know how much was the tip, we can set up a percent problem, but I want you to notice this is not 15%. Okay, if we set it up as 15% over 100%, and we try to find this, what we're going to find is that we were charged $31.05, but it actually cost us hundreds of dollars to eat this meal. And that's not true, okay? So what are we missing? We're missing the fact that $31.05 is not just the tip. It's not just the percent of the tip. It's also the whole meal. So we need to put that $31.05 equal to 115%. Now when we set this up and solve, we're going to go ahead and cross multiply and divide. And when we do that, I got $27 even. Okay. Now, so my answer is $27. Well, actually, it's not $27 because I was trying to set this up and I wasn't paying attention to what I'm looking for. So whenever I have a word problem, I like to check before I submit my answer. I look at what was the question actually asking. And if you look at the question was how much was the tip? Do you think that we tipped $27? No, that's too much. That's not the tip. That's 100%. What I need to find out is what the 15% was. In other words, I could either go reset this up and change this right here to 15% instead of 100%. I could do that, or I could take what I have here and subtract it from 31.05. So that's what I'm going to do. I'm going to take the 31.05 and I'm going to subtract 27. And what I ended up with is a tip of $4.05. Simon's monthly take-home pay after taxes is $2,400, and he pays 23% of his gross pay. That means gross pay is before taxes. Before taxes. That's what gross pay, before anything that comes out. Oh, it says it right there. Look at that. Before taxes and tax. So in other words, if 23% of his income, of his salary, is taxes, that means his take-home pay is 77% because it has to add up to 100. So I'm going to say take-home or after taxes. Now, we know a few things. We actually do know a few things, but what we want to know is his gross pay. And the reason we know that the take-home pay is 77% because the gross pay needs to add up to 100%. So we're going to go ahead and do a proportion to solve this. We don't know his gross pay. So that's what I don't know. But I do know his take-home pay. It's $2,400. So we can cross multiply and divide in order to solve that problem. Let's look at a percent increase problem. Now, when we're doing Unit 8, we gave you very straightforward math problems, but now what we're doing is we're trying to put them in context, real context for you. So in this example, we have Clint, and he has a salary, and he got a raise. Good for him. His salary increased from $21,000 to $35,700. So did he get a $35,000 raise? No, because we have to take his new raise, his new salary, divide it by his old one after we subtract it. And so what we see when we do that is we get Clint's percent increase. And actually we got 0.7. So as a percent, we'd say that's 70% because we'd have to move it 2 decimal places. Now, Helen also got a raise. Ellen got a raise all the way to $44,200, so even more money. But to be fair, Helen did start out already making more money. And so if we subtract those to find out how much money she made, well, she made how much money in absolute terms? In absolute terms, we'd say she made, oh boy, what is this? This is 20, no, not quite 20,000, but 18,000 for, no, 18,200. She got an $18,000 raise. That's fantastic. I'm happy for her. Now, if we were to subtract Clint's salary, he didn't make $18,000. So in absolute terms, what we'd say is Helen made more. She got a bigger raise. However, what we'll notice if we divide by what she started with, Helen has the actual same relative raise. And so they both got a 70% raise, but in absolute terms, Helen got more. So in absolute terms, Helen got more, but in relative terms, they actually got the same. So let's stick with this kind of negative topic when we're talking about cancer. And let's look at an example, and we're kind of connecting our counting tables with that idea of relative versus absolute, taking into context. So the first question says, suppose a patient has a positive mammogram. That's what it says. Suppose a patient. So if we look at our table, where are the positive mammograms going to show up? They're going to show up right in this row. So we focus on whatever row or column we're talking about. And then the next thing we do is we say, what section of that column do we want? And it says, what is the chance that she really has cancer? Okay. So cancer, when we say cancer, in this case, we're going to use the word malignant as interchangeable for cancer. That's not necessarily a one-for-one, but I wanted to use it anyway. And so what you'll notice is we've got that column and that row. And so we're going to use the 85 that's in both for our numerator, 85. And we're going to divide it by our total. But we're not talking about the absolute. We're not talking about the big picture, okay? So don't put 10,000 on the bottom. When we talk about total, we need to say, well, total of what? Total of the context. We said, first off, they have a positive mammogram. So the total that has a positive mammogram is right there, okay? So the total needs to be the context total. And if we go ahead and type that in, we're going to get our percent, okay? Let's look at another one. It says, what is the chance of a positive mammogram? What is the chance of a positive mammogram given that the patient has cancer? So what is my context? Is my context that they have a positive mammogram or that they have cancer? It says given, which is kind of our given is our given. Given is our giveaway for what we're looking at here. It says given that the patient has cancer. So that means we're going to start by looking right here. And it says, what is the chance of a positive mammogram? And so a positive mammogram is going to be right there. And so we can go ahead and answer our question with, again, 85. But our denominator this time is out of 100. Suppose a patient has a negative mammogram. Okay, so in our third example, suppose our patient has a negative mammogram. So I'm going to go to negative mammograms, and this is our category that we're dealing with. This is our context. And then it says, what is the chance that they have cancer? And so we're going to look for, well, that's just 15 people out of how many? Well, out of the 8,575 patients. So when we do these, what we're going to do is we're going to look and make sure we're paying attention to the context. It's not always what comes first. Notice that in this one, it's not what came first. It told us given gives us our context. I want to show you one more problem before I cut for the day. Okay, check this out. These are numbers in order. Okay, it's kind of hard to see that they're in order, but I want you to notice they kind of go down this way and then down in the second, down, down, down. Okay, so we can kind of see that they're in order. And what we have here is we've got a request. It says, go ahead and find Q2, Q1, and Q3. So first off, it puts them in a weird order. Why did it say Q2 first? Well, Q2 is what we're going to find first. Q2 is the median or the second quartile. So the median is our middle number. So if we kind of look in order, what we'll see is our middle number is going to be 480. That's the number exactly in the middle. If we look for Q1, what we're looking for is the lower quartile. And so that's like the median of the lower half. So if we look, this one's kind of tough, but if we go 1, 2, 3, our middle is going to be 420 on the lower half. Okay, it's halfway. It's the middlest number on the lower half. Okay, right about there. And then for Q3, when we look at the middle number on the upper half, we look at the middle number on the upper half. Which one are we going to see? And so I think what we're going to see is 1, 2, 3, 4, 5, 6. I think it's kind of in between these two right here, because I got 4 numbers here and 4 numbers here, kind of in between those two. So I might say that is 600. Okay. And so what we're trying to do is find the lower quartile and upper quartile and the median. If we look at statistics like mean, median, mode, and quartiles, they actually tell us a lot about the makeup of a population or a sample. In this case, we have all of the salaries of a company, but rather than give you all of the salaries, I just gave you some of our key details: mean, median, mode, first and third quartile, and then just for fun, I gave you the 93rd percentile. So the first thing we need to know is what the most common salary is. Now, I actually told you what it was if you know that the word most common is mode. And so the most common salary is 580. The salary that half the employees' salaries surpass. So half of them are above or half of them are below. I also told you that one. That one is the median. So that would be $500. Half of the employees make $500 or more, half of them make $500 or less. The percent of employee salaries that surpassed 585. Okay, so I want to look at where 585 is. 585 is right there. It's the third quartile. In other words, if you think about having 3 quarters, that's 25 cents, 25 cents, and 25 cents. And if we want to say above that, how many more quarters do you need to make $1? Well, you just need one more. And so the percent of employees is actually just going to be 25%. So we can think about quartiles like quarters out of $1. The percent of employees with salary less than the first quartile, less than 445. So if we look right there, and we have all 4 quarters as $1, the first quartile means just the first quarter, okay? How many of them are less than the first quarter? Well, how many cents do we have less than the first quarter? It's just 25% there. If I ask for more than the first quarter, we'd say, well, there's 75% more. The last question is that surpassed 701. Now, 701 is not exactly on a quartile. It's at the 93rd percentile. And what a percentile is it says that if 100% of the data is between here and here, if I put the 93rd percentile here, that means 93% are below that. So this actually doesn't ask below, it asks surpassed. In other words, what is the rest of it? What's above that 93%? And so our answer is going to be that 7%. Now we should do this at least once. We should do this frequency table. So the way this works is we're going to build a frequency table, and we're going to calculate the relative frequency and the cumulative frequency. So we've got our data up top. And what I'm going to do is first, I'm just going to make tally marks and build my frequency table with tallies. So I'm going to look 74, I'm going to cross it off, and I'm going to put a mark, a tally between 70 and 75. 72 also goes there, 89, 66, 97, 77, 69, 66, 96, 72, 82, 71, 98, 70, 64, 92, 85, 99, 76, 87. And so I end up with 4, 2, 3, 2, 5, and 4. Okay, and so those are my frequencies. How many times do we have a score in that range? And so we have it. What is my total amount of frequencies? Well, if I add those all up, 1, 2, 3, 4, I end up with 20. Okay, so when I do my relative frequency, what I'm going to do is I'm going to do 4 divided by 20, or 2 divided by 20, or 3 divided by 20, and convert that to a percent. And so 4 divided by 20 is 20%, 10%, 15%, 10%, 25%, and 20%. Now, double check that our relative frequency adds up to, yeah, it actually adds up to exactly 100. That's perfect. Now, when we talk about cumulative frequency, cumulative means how many do we have in this category? Or how many do we have in this category or any category before it? So we say in the first category, there's 4, right? But in the second category, there's 4 plus 2. There's the 2 in that category and the 4 that came before it. So we get 6. In the next category, there's 3 plus the 6 that we already had, so 9. And then we have 2 plus the 9 we already had, so 11. We have 5 plus the 11 we already had, so 16. And we have 4 plus the 16 we already had, which is 20. And the good news is we were supposed to add up to 20, so I like that.